Hello, 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 hello everyone. Today we shall discuss about uh, the term potential energy, and you see how. So we will discuss the potential energy and see how it works. So the potential energy can be defined in this way, right? So you see here how it works. And you will find that potential energy can be defined in this way. You see here that we are see how we find the potential energy and how we are defining the potential energy. So today we'll discuss about the concept of potential energy, and you see how concept of potential energy arises and how it can be defined. So let us see how the potential energy can be uh, defined. So here you can see that the potential energy can be defined here, the concept of potential energy, that is the concept of potential energy. The concept, today we will learn about the concept of potential energy, the concept of potential energy. The concept of the concept of potential energy, concept of potential energy, the concept of potential energy, the concept of potential energy. What is that? The word potential suggests possibility or capacity for action. So we learned some words about the potential energy. That is, the word potential suggests the word potential. The word potential suggests possibility, suggests possibility, possibility, suggests possibility or capacity for action, or capacity for action, or capacity for action. This is what you call it as potential, right? So this is the word potential suggests possibility or a capacity for action. Now you learn that the term potential energy brings to one's mind stored energy. The term potential energy, the term potential energy, the term potential energy, the term potential energy brings to one's mind, brings to one's mind brings to one's mind stored energy. Stored, you can say it, the potential as stored energy, right? Stored energy. That is the meaning of the term potential. A stretched bow string possesses potential energy. A stretched bow, a stretched bow, a stretched bow string possesses bow string. A stretched bow string possesses potential energy. Possesses potential energy. Possesses potential energy. Potential energy. So, a stretched bow string possesses potential energy, right? Not only that, when it is released, when it is released, when it is released, when it is released, the arrow flies off at a great speed. The arrow flies off at a great speed, We know all these things, and these are known as potential energy. The earth crust is not uniform. We know that the earth crust is not uniform, but has discontinuities and dislocations that are called fault lines. But has discontinuities, but has discontinuities and dislocations that are called fault lines, that are called fault lines These fault lines in the earth crust are like compressed springs. These fault lines in the earth's crust are like compressed spring, compressed spring. They possess a large amount of potential energy. They possess a large amount of potential energy. They possess a large amount of potential energy. An earthquake results when these fault lines readjust. An earthquake results. An earthquake results when these fault lines, when these fault lines, in these fault lines readjust, readjust. Thus, potential energy is a stored energy. Thus, the definition can be seen in this way. Thus, potential energy is stored energy. Potential energy is the stored energy. Potential energy is the stored energy. Potential energy is the stored energy. So potential energy is stored energy by virtue of which, by virtue of the position or configuration of the body, by virtue of the position, or configuration of a body, or configuration of a body. So we can find the potential energy as the stored energy by virtue of the position or configuration of a body. The body left to itself, the body left to itself, the body left to itself, the body left to itself releases this stored energy, releases this stored energy, energy in the form of kinetic energy, in the form of kinetic energy, Let us make our notion of potential energy more concrete. Let us make our notion of potential energy more concrete. So we learn what is that potential energy, and what the definition we got is this: the potential energy is stored energy by virtue of the position or configuration of a body. That is the potential energy. But now we learn in detail what is the meaning of potential energy. So we first try to understand what is the meaning of potential energy. Actually, the gravitational force on a ball of mass m is mg. We know that the gravitational force on a ball, the gravitational force on a ball of mass m is m into g. We know this one. That is the gravitational force on a ball of mass m is mg. G may be treated as a constant near the Earth's surface. Small g is acceleration due to gravity. G may be treated as a constant. Near the Earth's surface. By near, we imply that the height h of the ball Above the Earth's surface is very small. What is the meaning of by near? Actually, by near we imply by near we imply that that the height that the height that the height h of the ball height h of the ball above the earth's surface above the earth's surface above the earth's surface is very small is very small is very small is very above the earth's surface is very small compared to the earth radius 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 is RE, that is small h, is much less than that of radius of earth. That is the meaning of near. Okay, the gravitational force on a ball of mass m is mg. G may be treated as a constant near the mass earth's surface. By near we imply that the height of the ball above the earth's surface is very small compared to the earth radius. So h is much less than radius of earth. So that we can ignore so that we can ignore the variation of g, ignore the variation of g, ignore the variation of g near the earth's surface, near the earth's surface. In what follows, we have taken the upward direction to be positive. In what follows, we have taken the upward, direction to be positive, upward direction to be positive, upward direction to be positive. Let us raise the ball up to height h, up to height h, up to height h, up to height h. Up to height. Let us raise the ball up to height h. So what happens? The work done by the external agency, the work done by the external agency, work done by the external agency, work done by the external agency against the gravitational force, against the gravitational force, against the gravitational force is mgh. We've taken the height as upper direction to be positive. right? And so the work done by the external agency against the gravitational force is mgh. This work, this this work, this work gets stored as potential energy, gets stored as potential energy, as potential energy, as potential energy. Gravitational potential energy of an object. Gravitational potential energy, gravitational potential energy, gravitational potential energy, gravitational potential energy of an object, gravitational potential energy of an object is a function of height, as a function of height, as a function of height, as a function of height h is denoted by VH, and it is a negative work, and it is the negative of work done. It is the negative of work done, negative of work done by the gravitational force, work done by the gravitational force, by the gravitational force, by the gravitational force in raising the object to that height, in raising the object to that height, So you can write the pH is equal to mgh, right? So what are you getting? That pH is what? That pH can be represented as gravitational potential energy of an object as a function of height is defined. pH is equal to mgh. Mgh means potential energy. If h is taken as a variable, now you see here what we get, pH is equal to mgh. The potential energy depends on this height. The more the height, the more the potential energy, because mass and g is constant here. So what we find here, that if h is taken as a variable, 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 it is easily seen, that the gravitational force, that the gravitational force equals the negative, derivative of VH with respect to height, with respect to height. Thus we can say that a gravitational force is equal to negative derivative of d Vh by dh, dVh by dh, and that is equal to minus m into g. Right? So we are getting the force as minus mg. The negative sign indicates that the gravitational force is downward. Right? So we see that the force is acting downwards. This is minus mg. This is a ball, so this is minus mg. The force is minus mg. That is the, so dv by dh is equal to minus m into g. The negative sign indicates the negative sign indicates that the negative sign indicates that the gravitational force that the gravitational force is downward. The gravitational force is downward. When released, the ball comes down with increasing speed. When released, so you have to remember this one, that F is equal to minus dp by dh, right? And that is what you are getting, minus mg. The negative indicates the gravitational force is downward. When released, the ball comes down. The ball comes down. The ball comes down with an increasing speed. With an increasing speed. Just before it hits the ground, just before it hits the ground, just before it hits the ground, its speed is given by v square is equal to 2gh. The equation can be written as this equation can be written as half mv square is equal to half into m. In place of v square we write 2gh. So these two will cancel, and we are getting as mgh. So half mv square we are getting as mgh, which shows that the gravitational potential energy of an object at a height h, which shows that the gravitational potential energy, that the gravitational potential energy of the object, gravitational potential energy of the object, potential energy of the object at height h, this shows that the gravitational potential energy of the object at height h, when the object is released, the object is released. When the object is released. Manifests itself as kinetic energy. Manifests itself as kinetic energy itself as kinetic energy as kinetic energy as kinetic energy as kinetic energy of the object on reaching the ground. Itself as the kinetic energy of the object, kinetic energy of the object, kinetic energy of the object on reaching the ground. So one form of energy is converted to another on reaching the ground. So one form of energy is converted to another form of energy. First it was the kinetic energy, was the potential energy. Before it hitting the ground, it converted into kinetic energy. Right? In this way you can explain the potential energy. Physically, the notion of potential energy is applicable only to the class of forces where work done against the force gets stored up as energy. That is potential energy. You see here, so you can say that physically the notion of potential energy, the notion of potential energy, the notion of potential energy, the notion of potential energy is applicable It is applicable so you are writing it as applicable only applicable only to the class of forces where work done against the force gets stored energy it is stored energy or it can stored up as energy. That can be also written in this way, that is stored up as energy. When external constraints are removed, it manifests itself as kinetic energy. When external constraints are removed, it manifests itself as kinetic energy. And here you can say that one form of energy is converted into another form of energy. That is, potential energy is converted into kinetic energy. Mathematically, for simplicity in one dimension, mathematically, for simplicity in one dimension, for simplicity in one dimension, simplicity in one dimension, the potential energy, the potential energy Bx is defined if the force Fx can be written as Fx is equal to minus dv by dx. Okay, or this implies that Fx is equal to minus dv by dx. This implies that integral x initial to x final fx dx is equal to minus integration of v initial to v final dv, or v final minus v initial. Minus v final minus plus vi, that is vi minus vf, vi minus vf, right? So we got this mathematically. Fx dx is equal to minus dv, or v initial minus v final. The work done by conservative force such as gravity depends on the initial and final position only. The work done, that's why gravitational force is called a conservative force. The work done by conservative force, force such as gravity depends on the initial and final position only. So you can say that gravitational force is a conservative force because conservative force depends on the initial and final positions only. Right? So you can say that gravitational force is a conservative force. Besides that, the total work done at closed path is also zero in case of conservative force. In the previous chapter, we have worked on examples dealing with the inclined planes. If an object of mass m is released from the top of a smooth inclined plane of height h, its speed at the bottom is √2gh irrespective of the angle of inclination. Thus, at the bottom of the inclined plane, it acquires a kinetic energy mgh. If the work done or the kinetic energy did depend on other factors such as the velocity or the particular path taken by the object, the force would be called non-conservative. And you know that now in non-conservative energy, it depends on path, and the total work done in a closed path is not zero in case of non-conservative forces. The dimension of potential energy are the dimension of potential energy are the dimension of potential energy are m L square t to the power minus 2, and the unit is joule. The same as kinetic energy or work. The same as kinetic energy. Same as kinetic energy or work. To reiterate the change in potential energy, for a conservative force, for a conservative force del phi is equal to the negative of the work done by the force. Del phi is equal to minus fx del x. So if you remember this one, the change in potential energy for conservative force del v is equal to the negative of the work done by the force. The minus fx, that is del v, change in potential energy. In the example of falling ball considered in this section, we saw how potential energy was converted to kinetic energy. This hints at an important principle of conservation in mechanics, which we now proceed to examine. So you can say that this hints in the example of falling ball considered in this section, we saw potential energy was converted to kinetic energy, and this hints at an important principle of conservation in mechanics. Conservation in mechanics, which we now proceed to examine, which we now proceed to examine. Let's examine this one, that is the conservation of mechanical energy. So what we found that one form of energy is converted to that of another, and what we find, the change in potential energy for the conservative force del V is equal to the negative of the work done by the force. Del V equal to minus Fx del x, the work done. Del V equal to change in potential energy is equal to work done for a conservative force. Now we will find the conservation of energy. This one is also very much important for us, the conservation of energy. Now see here that the conservation of energy, the conservation of mechanical energy. Now we will prove the conservation of mechanical energy. The conservation of mechanical energy. The conservation of mechanical energy. So here we find how the conservation of energy takes place. And here what we learn, that is, for simplicity, let us demonstrate the conservation of mechanical energy. Here you find that for simplicity, we demonstrate this important principle, for one-dimensional motion. For one-dimensional motion, for one-dimensional motion. Suppose that a body undergoes displacement del x under the action of a conservative force F. Then from the work energy theorem, work energy theorem, we have, what is that? That change in kinetic energy is equal to Fx del x. The work done is a change in kinetic energy, right? And if the force is conservative, if the force is conservative, the potential function, the potential energy function the potential energy function Vx can be defined such that minus del V is equal to Fx del x. So the minus change in potential energy is equal to work done, and change in kinetic energy is equal to work done. Both are same actually. So this is from equation 1 and 2. From equation 1 and 2, from equation 1 and 2, we get change in kinetic energy is equal to minus change in potential energy. Or you can write change in kinetic energy plus change in potential energy is equal to 0. Or you can change in kinetic plus potential energy is equal to 0, which means kinetic and potential, the sum of the kinetic and potential energy of the body is a constant, right? So you can say, which means that kinetic energy plus potential energy, the sum of the kinetic and potential energies of the body and potential energies of the body is a constant. We get the sum of kinetic and potential energy of the body is a constant. So we can define, so the quantity, the whole path, over the whole path x initial to x final. This means that kinetic initial plus potential xi is equal to kinetic final plus potential x final. The quantity K plus Vx is called the total mechanical energy of the system. The quantity K plus Vx is called the total mechanical energy, total mechanical energy of the system. Total mechanical energy of the system. Individually, the kinetic energy and the potential energy may vary from point to point. Individually, the kinetic energy K, the kinetic energy K, and the potential energy Vx may vary from point to point, from point to point. But the total energy is always constant, and this is mechanical conservation of energy. But the sum is always constant, but the sum is a constant, is a constant. The aptness of the term conservative force is now clear. The aptness of the term conservative force, of the term conservative force is now clear. Now we'll say there's some definitions of conservative. Let us consider some of the definitions of conservative force. Let us consider some of the definitions of a conservative force. Or these are the some characteristics you can see of conservative. Number one, a force Fx is conservative. A force Fx is conservative. A force Fx is conservative if it can be derived. If it can be derived from a scalar quantity Vx by the relation del V is equal to minus Fx del x The change in potential energy is the work done. Change in potential energy is the negative work done, right? Change in potential energy, negative work done, right? The three-dimensional generation, the three-dimensional generalization requires the use of a vector derivative which is outside the scope of this book, which is outside the scope of this derivation. So what we got here is a del V equal to minus V, that is change in potential energy is the negative work done and change in kinetic energy is the work done. That is the difference, right? So number 2, this is the first characteristics of conservative force. And the second characteristics of conservative force is this one, number 2. Number 2 is the work done by the conservative force, the work done by the conservative force, the work done by the conservative force depends depends only on the end points, only on the end points. This can be seen from the relation. This can be seen from the relation, seen from the relation. W is equal to Kf minus Ki, that is equal to Vxi minus Vxf minus Vxf. The changing kinetic energy, this is Vxi minus V, this is because this is negative. Changing kinetic energy, this is changing kinetic work done, and this is changing potential energy equal to minus work done, right? So which depends on the end point, which depends on the end points, right? End points. This is the characteristics of conservative force. And the third one, the third definition states that a third definition states that the work done by this force, the work done by this force in a closed path is zero. In a closed path is 0. So you can say integration of W is equal to 0. This is once again apparent from equation 5.6 etc. Thus, the principle of conservation of total mechanical energy can be stated. Thus, the principle of conservation of total mechanical energy can be stated as the total mechanical energy of a system is conserved if the forces doing work on it are conservative. If the forces doing work on it are conservative. From here you can also say that gravitational force is a conservative force. Now we can see what we get, that the above discussion can be made more concrete by considering the example of gravitational force once again, and that is the spring force in the next section. In this figure, you'll find a ball of mass m is being dropped from a cliff of height. Let us prove this mechanical conservation of energy. This is suppose a height. We have taken a height here. This height is suppose h. From this point to this point, and from here to here this is h, this height is h. Therefore, you are getting velocity here as 0 and here velocity Vh and the V, here V as V final. So, we'll find the energy at point A point, at B point and C point. Let us find what is the total energy, right? So, let a ball of mass, let a ball of mass m, a ball of mass m being dropped from a cliff, of height capital H. The total height, we take it as capital H. This height is taken as capital H. So, the total mechanical energy, mechanical energy E0 EH at height 8 and capital H of the ball at the indicated heights, H and capital H are E energy at this point, A point, is mgh. This is equation 1. At this point, that is E, capital E at a height small h, that we are getting the value at mgh potential energy plus kinetic energy half m velocity at a height h square, and E0 means at the ground level is 0 equal to half m v f final velocity final square. This is 1, this is 2 and this is 3. The constant force is a special case of speciality dependent force Fx. The constant force is a special case of a spatially dependent force Fx. Dependent force Fx. Hence the mechanical energy is conserved. Hence the mechanical energy is conserved. Thus, EH is equal to E at 0. This energy is same. Or EH is how much mgh and E0 is half mvf square, half mv final square. Or you can say, or this shape cancel, vf is equal to root 2 gh. Result that so vf we got root 2 g. This is 4, equation 4. What we get for a freely falling body? We get this equation 4 for a freely falling body, falling body, we get this one, that is Vf equal to root over root 2 GH. Further you can say, further EH is equal to capital E in small h, which implies EH means mgh is equal to E small h means mgh. EH is the capital H, it will be capital H, that EM capital H mg capital H is equal to energy at height h is mgh plus half m vh square. From that m will be cancelled, so we are getting gh is equal to gh plus half vh square, or you can write it here as the gh is equal to these 2gh plus vf square, and this will be multiplied, so we are getting 2gh is equal to 2g small h plus vf square, or you can write vf square as vf final, we are writing as h, not f, vh, velocity at height h is equal to, we are getting 2gh minus 2gh, or vh square can be written as 2g into capital H minus small h, right? And a familiar result from kinematics, and a familiar result from kinematics. At height h, the energy is purely potential. At a height h, at height capital H, the energy is purely potential. It is partially converted to, partly converted to kinetic energy at height h, and is fully kinetic at ground level, This illustrates the conservation. This illustrates the the conservation of mechanical energy, Thank you everybody for watching this video.